in your midterm exam, which is in the chapter 4. 4.4 and 5. Okay, this is the one I really think you need to concentrate on this, and I want you to work with me step by step. Right. So the section 4.4 is balance on a multiple unit processes. So just now we learned this, right? This relation column, you have input and output, one input and two output, and you can do input equal to output to get these four unknowns, right? Four unknown variables. Okay. What happens if I give you something like this? There are multiple unit processes, and I give you many unknowns. You might say, "Wow, Professor, I give up." No, you don't. You are a top 10% high school student, right? So you don't give up. So you need to find out how to solve this problem. And I'm the one who help you to solve this problem. So you need to work with me step by step. Okay, so let's start from the most easy one, 2 units. Okay, 2 units. So assume you have fit 1 here. If you have fit 2 here, you might say, well, why this fit 2 is not in this unit 1? I just want to give you trouble anyway. And you need to find out, and you need to know why it works like this. Assume there are 2 pipes. You just connect these 2 pipes together to the reaction, unit 1. It makes sense, right? But anyway, you just follow the flow chart, and you don't know what's unit 1. So you have one output, which is product 1. Because this stream doesn't go to the unit 2, so it come out will be, input will be feed, output will be product. So this is product 1. Okay? So of course you have unit 1, and because the things isn't completed. Okay, so this string go to the unit 2. So you have product 2 come out in this way. You really don't know what's going on. Actually, you don't care what's going on inside the black box. You don't care. You just care. You just need to know input equal to output. So the feed 3 into the unit 2, and you have product 3. Okay? So this is the process looks like. So how many inputs? So if you take this as a system, you know, if you have a hypothetical box, 假想 hypothetical box here. So how many inputs in this process? How many input streams in this process? There are 3 inputs in this process, right? Feed 1, feed 2, and feed 3. Okay, how many outputs in this process? There are 3 outputs. Product 1, product 2, product 3. So assume you have 3 species. You have 3 species, A, B, C. You have to use A input in the feed 1, feed 2, feed 3 equal to the A output from product 1, product 2, and product 3. This is one equation. Okay? Okay, apart from this system, apart from this hypothetical box, how many systems you can create? This is system 1, right? Of course, you can have system 2 here. How many inputs? There are 2 inputs from this box, right? This is you can regard this as a mixer, right? Here, if there are 2 pipes connect together, it can mix A and B, right? The pipe A is a A species, pipe B is B species. So there's a junction, there's a connector, connect A and B. So you have a mixture of the A and B to the output. So the feed A and feed B here, and how many output streams? 1 output stream, this one, right? Okay, this is system. This is what we call single unit system. Single unit system. Number 3, this is single unit system. And this is what? Splitting. This is join, right? This is split. You have 1 pipe split into 2 streams. So you have splitting point. Okay, this is single unit number 4. And number 5, this is single unit. Okay, what else? You might say, well, this is overall. So, Professor, can I have 2 units, 2 single units together? Yes, you can. As an assistant, yes, you can. You can put these 2 together, that will be something like this. Okay, so if you want to do input equal to output, this is more complicated. So the system, the concept of system is that, in general terms, a system is any proportion of a process that can be enclosed within a hypothetical box. This is, as I just have a dashed line here, right? Dashed line here, this is called hypothetical box. So it may be what? As I just told you, entire process, this is entire process, right? Or in the connected combine of the sum of the process unit. Yeah, unit 1, unit 2, or unit 1, joint splitting point, and this one. A point at which 2 or more process streams come together, right? 2 or more streams come together, something like this. Or one string split into a branch, this one. Okay. Okay? Right. So the point 1 here is entire process, which is feed 1, feed 2, feed 3, remember? And the output is product 1, product 2, product 3. Feed 1, feed 2, feed 3, product 1, product 2, product 3. And how about point 2? Feed 1 and feed 2, right? And then what? The output is the stream flowing to the unit 1. This one is the one. Okay? Right. So material balances calculation on a multiple unit process. Let's say that basically the same as the single unit process. It's very easy, simple. Input equal to output, DOF. And then 4 directions to find out equations. Remember? So isolate and write balances on several subsystems of the process. And then degree of freedom analysis first. Because, with a single unit process, it's easy to do DLF. But if you have if you have 4 units in these processes, and then it might be more complicated to do the calculation. And you need to do degree of freedom analysis first. Okay, this is the example to showing you that a 2-point unit process, it looks like this. This is the information we know from here. So we just write down the information we don't know from this process. So as you can see, this is the total amount. This is the fraction. Total amount, fraction. Total amount, fraction. Total amount, fraction. So you have this. You don't know this stream. The information about this stream. You don't know the information about this stream, and you don't know information about this stream. So you write it down. So this time we write down the fraction. M1 is the total mass in the output stream of the unit 1, and this is the x1 is a fraction of the A. 1 minus x is fraction of B. You might say, well, Professor, why this is not unknown? Of course, this is not unknown. And this is non-variable because this the fraction A plus fraction B equal to 1. So if A is x1, of course, this will be 1 minus x1. This is not unknown. This is known if you got the answer of x1. Okay, so as a result, this string only have 2 unknowns or 2 unknown variables. And this is the output of this joint point, which is m sub 2 over dot, right? Well, remember what is the meaning of over dot? Flow rate, right? The mass with time. Mass divided by time. Okay, again, you have fraction here. So can you solve this? Can you get the answer of these 6 unknown variables? Can you? DOF, right? If you know how to do DOF, you can get this. You can tell me. You don't need to do calculation. You can tell me, you can get this answer, you can get the value of this 6 unknown or not before you do the calculation. Right? So DOF important. So let's do it DOF first. So basis, 9 steps, right? Remember 9 steps. First step is basis. Basis is what? 100 kilogram per hour. And then flow chart. You draw the flow chart and write down the knowns and unknowns. Okay, so steam 1, steam 2, steam 3. Okay? Okay, how many systems? Can you tell me how many systems here? So this, this is one, the information we got, and this is the systems. Tell me how many systems. Of course, you start to do first, easy one, overall process. This overall process, this is one system, right? Number 1 system. And do it easy way, single unit system, single unit. 1, 2, 3, right? 1, 2, 3. So there are 3 single unit systems. How many 2 single unit systems? How many? 1, 2, right? There are 2 single unit systems. Sorry, there are two single unit systems. Okay? Are you with me so far? Yes, right? No problem. Okay, so as we know, you can create so many systems. So which one you want to go first? You want to go from overall input equal to output, or single unit input equal to output, or you want to go to 2 unit system input equal to output? Of course, you do an easy way first. So once you see that, overall DOF, can you do overall DOF? Yes. How many input? Could you please tell me how many input? How many input streams? How many input streams? Yes, it's very important for you to do the calculation. How many input streams? 2 input streams, right? This one and this one. How many output streams? How many output streams? 3 output streams, right? 1, 2, 3. Okay, so need to do A input stream equal to A output stream. Okay, then how many unknowns in this box? In this outside of this box, hypothetical box, how many unknowns? 2, right? Because these are only 2. This is inside the box, so you don't do the calculation of input equal to output. So there are two unknowns. Okay, so DOF is what? 2. And please tell me how many equations you can have. 2, right? Because there are 2 species, A equal A and B. Okay, do you have any specification? No, I didn't tell you any specification. Do you have physical laws? No. Physical constraints? No. Just like the Kahoot we had, right? Okay, so you have 2 unknowns, 2 equations. So 2 minus 2 equal to 0. Bingo, you can get answer of M3 and X3. Okay? So 2 unknowns, 2 equations. So you can get M3 and X3. You can game, okay? So, yes, you got the answer of these 2. How about if you go to mixing point after that, after the overall mixing point? How many input streams? How many input streams? This point, you use a small box. How many input streams? 2 input streams, right? This input and this input. How many output streams? This one, output streams. How many unknowns in this outside of this box? 4 unknowns. M1, X1, M2, X2. Okay, how many equations you can create? 2, right? Because you only 2 species, A and B. So 4 minus 2 equal to 2. I'm sorry, you cannot get the answer of these 4 variables. Right? Right? Okay. So, bad news. Is that true? You cannot get answer of these 4? No, you can get answer of these 4, but you don't want to use this system. You want to use other system. For example, if you use this system, you get these 2 answers first. And once you get these 2 answers, you can get these 2 answers. Right? Okay, try another system. So unit 1, you can get this, right? You go back to this, you can solve this. So now you solve this and this, and then you can go back to this. So, and then after that, you know, wow, Professor, I can get this. Okay, according to DLF, I can get these 4 unknown variables. So I do the calculation now. Again, I don't want to waste your time, so please practice this by yourself. So this summary. Summary is that once you have a multiple unit system, you have to count how many systems you have. First is overall process, right? Second is individual units process or systems. Third is combination units. It can be 2 combination unit system. It can be 3 combination unit system. It can be 4. It can be 5. And you need to do computational efficiency, right? Solve the equation which has less unknown first. Okay, so this is the exercise. This is the practice. This is the example we want to do. We want to practice, which is liquid-liquid extraction, and this will definitely in your midterm exam paper. I will say absolutely. So please, I don't want to fail you. honton히, I don't want to fail you. So please, okay, do this, practice this when you you can work with me now. But before we really do the input calculation of input equal to output, I want you to know what is liquid-liquid extraction. Or in the example of 4.4-2 is an extraction distillation process, which is the combination of extraction, liquid-liquid extraction, together with the distillation. So I already tell you what is distillation. Okay, so what is water process? This is the example of water acetone mixture. Before that, I think I show you what is. Do you know extraction? No, okay. Let me do this one by one. So, for example, you have water and acetone together. If you want to separate water and acetone, you might say, "Well, Professor, I just learned distillation is a good tool to separate two liquids with a different boiling point." But unfortunately, this water and acetone, the boiling point is too low. For example, acetone, a boiling point is 56.53. You cannot separate these two by distillation so well. So this is the molecular structure of the acetone. Oh, sorry, what's that? Okay, so acetone is kind of very good solvent. It's a colorless, mobile and flammable. It's like alcohol. You can burn this. Okay, it's a good solvent. Okay, this is a good solvent with polar bonds. Mixable with water. It can be mixed with the water very well. So when you mix the water and acetone, it looks like this. It's clear. You don't. It can be water is clear, is transparent. Acetone is transparent, and you mix it up. It looks like this. So how can you separate these two? Using this? No, you cannot, because I just told you boiling point is too low and too close. So the best way to do this is as a distillation column is not good. So this is the molecular structure of water, molecular structure of acetone. So we want to use liquid-liquid extraction to take these two apart first, to separate these two. So we introduce the third, we introduce these two, we introduce the third molecular, or we introduce another agent to separate these two. You know, it's like Ch4.4, okay? If you water and acetone are very good, you know, they mix it very well. You marry coupled. Ch4.4 come, okay? This Ch4.4 is MIBK. MIBK, the boiling point is 116 Celsius. So as you can see, wow, if Ch4.4, sorry, if MIBK, I'm sorry for the girls, I should say 小王, okay? Ch4.4 is 小王, whatever. So they introduce, you can, this is MIBK. So MIBK can dissolve acetone, cannot be dissolved in water. So if you put the MIBK into this mixture, the MIBK will take out this one, will take out acetone. Okay? So you can do the separation of water and acetone by liquid-liquid extraction. Again, I want to tell you is that this mixture, I introduced MIBK into this mixture, and MIBK will dissolve into the acetone. So you take this apart. You might say, well, Professor, what happened? I get water, but acetone still in the MIBK. And you can, as you can see, MIBK, the boiling point is 116. The acetone, the boiling point is 56. So I can use distillation to separate these two. So there are two processes. First one, liquid-liquid extraction. Second one is distillation. I don't want to do this in the laboratory. I want to do it in the industry, in the engineering point of view. I want to do mass production of this, or mass separation of this. Okay, so this is liquid-liquid extraction, and then I do the distillation. Okay, so MIBK, what is MIBK? MIBK is the molecular structure looks like this, and it's also used heavily in the industry. It's a flammable, colorless liquid with a kind of smell. Okay, and it's a kind of solvent and a quite low solubility in water. It doesn't solute in water, but it's a good organic solvent which can solute in the acetone. So we can use liquid-liquid extraction to separate acetone and water using MIBK. So widely used as a solvent for this kind of nitricellulose, lacquers, and certain polymer and resin. So anyway, you just remember this is a kind of solvent. So what is liquid-liquid extraction? Do you do this liquid-liquid extraction in your high school, in chemistry class? No? Ch4.4, have you heard about this? Ch4.4, liquid-liquid extraction. So liquid-liquid extraction is a method to separate the compounds based on their relatively solubility. In the distillation, we use volatility to do the separation, and now we don't do volatility, we do solubility to separate two compounds in two different miscible liquids, usually water and organic solvents. Okay, it's an extraction of the substance from one liquid phase to another liquid phase. So this is widely used. Liquid-liquid extraction is widely used, even including nuclear reprocessing process. Okay, or oral processing or production of the fine organic compounds. Or when you want to make girls' perfume or men's perfume, you also use this liquid-liquid extraction. Okay. So this is liquid-liquid extraction, and then, you know, when you take out caffeine from your tea or from your coffee, you also use extraction, okay, by different chemicals. Okay, so have you, you know, like my wife doesn't like, cannot have coffee in her tea. So some of the, like Darjeeling or something, the tea, red tea Darjeeling or Earl Grey, is, you know, some of products we allow the caffeine, right? So you can have that. Okay, so I want to show you what is, before we move to the information again. Right, I think, let's say for today, do you have any questions for me? No, good. So I hope you enjoyed the lecture today, and I will see you on Wednesday.